So in this structure, we're going to be dealing with solvents. So you should have opened the HPD168R.res file. And if one thing you should notice differently in this data set is that in this data set, we use copper K alpha radiation. So if you check here, it says CU, where in the past, we've been using moly data sets. So this is the first time we're using a copper data set in our practice session. So the I over sigma is not bad, 27.2. Completion is good. And notice the difference in the 2 theta for completion. With moly, we saw up to about 70 to 80, 60 to 70 degrees 2 theta. With copper, we can see, anywhere from 140 to 150-ish in that range, 2 theta. So we get higher 2 theta when we use copper. So again, the first thing we need to do is solve the structure. So you want to select the program you want to use. So I'm going to be using SHELX. As far as the Z, I like to put the Z such that Z prime starts out as 1, and then we can always go back and correct it if it's not right. So I'm going to change Z to 2 because again, this is P1 bar. There are 2 symmetry operators, so to get a Z prime of 1, we need Z to be 2. Click on suggested space group. Again, we get P1 bar and P1, a centrosymmetric, non-centrosymmetric space group. So we'll stick with P1 bar. So we click solve. Now this is an organometallic complex. So it contains iron, it contains carbon, oxygen, and hydrogen. So this is our initial structure. And so the iron or the iron ions are in the correct location. And this is the kind of the organic molecule that is coordinated to the iron. So you see here we have some carboxylate groups here and here that coordinate to the iron. And then this hydroxyl group here that coordinates to the iron. So those are all the key coordination sites for this organic ligand. Now, as we look at the rest of the structure, let's first zoom in and look at this entity here. So obviously, it doesn't make sense that this is a carbon atom that is coordinated to 2 iron sites. So what we're going to do is maybe, and again, one of the solvents used in this in the crystallization was methanol. So maybe what we have here is a methanol molecule coordinating or bridging these 2 irons. So what I'm going to do here is I'm going to change the atom types. So this one I'm going to change to oxygen. And this one I'm going to change to carbon. That makes more sense than having a carbon bound to 2 iron. So again, methanol was used in this crystallization process. So now also, if we look, that's good for now. Now let's do a refine. Make sure you clicked ACTA so that you create your CIF file. Number of cycles, not 11, but there we go. And let's click refine. So now we have this molecule up here that shows 2 carbon atoms. And so we need to model that next. So now if we look at this molecule here, it should be a methanol. And so to figure out which one is the oxygen, let's go ahead and first change this to an O. As we look at the bond distance, it's about 1.45. This is a methanol molecule. And now let's click refine. And you'll notice here in the center, this water molecule or this oxygen atom is extremely big. This tells you it doesn't like being 100% occupied by this oxygen atom. And so what we're going to do is we're going to decrease its occupancy. What you do is you right click, go to occupancy, and let's decrease it from 100% to 50%. Because since it's very big, it's telling you that it doesn't like to be 100% an oxygen atom 100% of the time. So maybe it's not there all the time, it's only there some of the time. So again, you right click, chemical occupancy, 1 means 100, 3/4 means 75%, 1/2, 50%, etc. So now let's click refine. And since we decreased the occupancy, it's going to decrease in size because now it's not there 100% of the time. It's only there 50% of the time. If it made it too small, then maybe we should go back and put it 75%. So you just have to play around with the occupancy. So one last thing we note that we still have some heavy peaks. We have a max peak of about 6.2. And if we see here that max peak of, the highest Q1 is near an iron. So maybe this will be taken care of when we do anisotropic refinement. So I'm going to go ahead and do that next. Model ANIS. And so you see now that we've done the ellipsoids are now representing the atoms and not spheres. You can see there's a little bit of disorder in this structure because the ellipsoids are a little bit elongated. You also notice that the ellipsoids on this methanol are a little bit big. So this would be an indication that you could reduce the occupancy of this methanol atom. So I'm going to reduce it to 1/2 first to see how it refines. And so it looks a little bit better when it's at 50% refinement, but our R factor went up just a bit. So I'm just going to go back and try it at 75% occupancy. And we'll come back to this in a second. If you see triangles on any of the atoms that you change, triangles mean that it's a negative thermal parameter. So either the occupancy is too little or you have the wrong atom type at that position. So triangles are not a good sign. So now we still have a max peak of about 1.4, and that's this here, which is about 1.397 from O12. So Q1 has a bond distance of about 1.4 from O12, which would suggest that this is a carbon atom. So it's another molecule of methanol. So I'm going to change it to carbon. Now the ellipsoid is pretty elongated, so let me decrease the occupancy here so that it kind of helps better model the oxygen atom. And so I really like that. We went to 23.3%. This was at 50% occupancy. So let's go ahead and change the other one to 50% occupancy as well. Still doesn't like it, but it looks better at 50%. So now this one carbon atom that's not anisotropic, if you select the carbon atom and go to model anisotropic selected, it'll only model that particular atom. So now we hit refine. And now we have the anisotropic. So next step, we're going to add hydrogen atoms. So we can just click add H. And it automatically refines it. Shown here. So it looks pretty good. So these methanol molecules hydrogen bond to the carboxylate groups. This water molecule hydrogen bonds as well. Refine one more time. So obviously the water molecule, the hydrogens on this water molecule are not being cooperative because you see our shift parameter is not convergent. So what we could do is we can try to constrain these hydrogen atoms so that they're pointing towards the oxygen atoms, and that might help the shift. So what we're going to do is if we click on this hydrogen and this oxygen, and we're going to do a restraint, a defix, and we're going to set the defix to about 2.1. Remember, hydrogen bonding between the oxygen and the hydrogen, it can be anywhere from about 1.5 up to about 2.5. So we're going to start with about 2.1 and see if how that helps the shift, because right now my shift parameter is pretty high. We're going to do it for the other side as well. Work, refine. And we're going to see if this is a good adjustment to the model. So now it looks like our shift parameter is converging. Let me do another refinement. Looks like we did a good job. So now that water molecule is kind of fixed now. So now we're good. We've constrained those hydrogen bonding distances, and our shift parameter has gone to 0. So as far as the model, it looks fairly good. So we do have some residual electron density with max peak of about 1. We could, it doesn't look like the masking solvent mask would work here. But I'll come back and show you another way to handle the solvent mask. Make sure to update your formula as well. So the next thing we want to do is now dealing with the weighting parameters, the 2 theta arranged. If we go to info, before we check the bad reflections, let's check I over sigma. And so here we see that we have up to 138 2 theta. It's still pretty decent quality data. So for copper data, 135 is the minimum cutoff. So if you go below 135, then you have to give some explanation as to why you went below the minimum data cutoff. So for moly, it's 50. For copper, it's about 135. And so generally with copper, I usually don't cut off data because the quality of the high angle data, the high angle data is very good quality. And so there's no need to cut off. So I'm not going to do any omit commands here. But what I will do is I will check for any bad reflections and omit those. So this is one bad reflection here. So if I click omit, it'll omit it from the reflection file. And so we still have this heavy peak here. This may, when we do a check SIF, cause an issue. If it does, we'll resolve it at that point. So now I'm going to work with the weighting parameters. I don't like the ones suggested here, so I'm going to go manually and change them in the instruction file. So edit, instructions. And so the first weighting parameter I'm going to decrease, say about 0.07, and put the second one at about 1.5, just as a reference point. Click refine. Check any bad reflections. So now I'm just playing with the weighting parameters until I'm happy. So we have some bad reflections here. Let's omit them. Now see, if you've noticed when I'm refining, this water molecule here is giving me trouble. So it's unhappy what we did. It's not staying connected. The shift, So it's moving out. We may need to address that in just a little bit, but let's see if we can get it to converge. So we bang here, 2.11. Change this. So what I'm going to do with the 0.005, I'm going to increase this to about 2.2 and see if that helps. That helped because we were forcing that hydrogen bond to be 2.1 and it wasn't 2.1. So that's why it's was disagreeing with us. So it's still being a pain, this water molecule. We'll try a few more things, see if it converges. If not, we'll go to our last option. So let me work on the there we go. So what I did is I just increased this oxygen atom to occupancy 1 just to see how it would affect the R factor. And I'm going to do the same thing here. We see we get a better fit to the model. This is just telling us that these solvent molecules are disorders. So I'm going to do the same thing with the carbon, increase it back to 100% occupancy. And hopefully, since it's solvents, we shouldn't see an issue with the check sieve. So we have some very disordered solvent molecules here. This one I have to reduce. Let's see, back to 1. All right. Nope, doesn't like it to be 1/2. Let's change it back to 1. Not cooperating with us. Take that. So again, it looked better when it was at 50%. Let me just try 75% occupancy. So 75% was agreeable. Let me try 75% for this. Again, this is all just, you got to try different things, see what helps improve the model. So it liked it at 75%. Let's see if we can get it to converge. And so this is the oxygen that I believe is giving us problems on the convergence, these hydrogens. So let me just check this. I'm going to delete this hydrogen here and see if that helps in the convergence. And let me delete this hydrogen. So still not converging. Let me just delete this altogether. So this electron density peak, we were having a hard time modeling it. Let me try to remodel it. There we go. You see, when I put the hydrogens on it, it's not doing what it's supposed to be doing. So if we wanted to, we can just, for illustration purposes, let's just delete it, refine it. And now we're going to do a solvent mask. So let's see if we can just squeeze out that electron density, because it's a little bit complicated or a little bit challenging to model. And we can explain it's going to be half a water molecule in the asymmetric unit. So when we did that, we were able to remove the electron density from the crystal lattice. Now this is about 8 electrons that it found. One water molecule is 10 electrons. So this is probably like 3/4 of a molecule. So we can say here in the explanation 0.75 H2O. And so it'll make that comment in the CIF file. So we tried to model it. It was giving us problems. We used the solvent mass to squeeze out that electron or mask that electron density. And it was about 8 electrons, which is approximately 3/4 of a water molecule. So if you were to look at a series of unit cells, 75% of them would have the water molecule, 25% would not. So now let's refine this. You can uncheck update mask and just keep the use solvent mask. Check the bad reflections, none. All right. I'm going to go back and set this back to 50% occupied and see if that does uh, anything better. No. Try this. So now I'm just going to do the oxygen 75%, carbons 50%. So we use the solvent mask when we can't model the electron density for the solvent. And so typically, since these solvents are coordinating to the actual complex, you would want to include these if you can, because if you were to squeeze these out, then you'd be missing this important feature in the crystal structure. Mm. Methanol molecules are definitely giving us a run for our money. Let's try custom. I'll put it at 80%. Oh, shabam. That looked good. So I put it at 80%. Let's see if it converges. Uh, Not quite, not quite. Close though, close. Let's try 85%. Let's try 70%. Getting there. Let me increase the number of cycles here, see if we can get it to converge. So what I did is I set these methanol molecules to 70% occupancy. And it looks like, cross your fingers, we're going to get some convergence for this. Almost there. One more should do it. Two more maybe. So we use the solvent mass to kind of mask the electron density associated with that water molecule situated here because we couldn't quite refine it. But for the methanols, they weren't 100% occupied. And after messing with the occupancy, we found that 70% seemed to work. And so what you do is if you right click, you can actually customize your occupancy. So 0.7 refers to 70%. And now everything looks good. If we refine one more time, cross your fingers, it'll go green. And now if we go just check info, any bad reflections, there's one. Let's omit it. So this was the first time I've actually, since solving this data set, I actually did this as a practice example. So I was a little bit nervous there for a little bit. Now we go to report. The crystal, this you get from the SIF OD file. So I'll go ahead and look up that information. So after entering in the crystal information, the fraction information, and the absorption correction. We did another refinement, and now we can do a check SIF. So cross your fingers. Hopefully there's no serious errors associated with it. And that's one of the things with when you're solving a crystal structure, you may have to go back and forth like we did on the occupancy for the methanol molecules until we found, I guess you call it the sweet spot where it worked. So it wasn't 100%, it wasn't 50%, it wasn't 75%. It looked like overall it ended up being up around 70% occupied. So we found the right occupancy for those molecules. So now let me share the check SIF file. So here they have a Z of 1, we have a Z of 2. Missing cell measurement reflections, I showed you how to correct those in a previous video, so that's very easy to correct. Now this Hirschfeld test difference, COOC, COU, this means that, hey, we need to check the ellipsoid size and see if we maybe missed labeled an atom here. So let's go back and quickly look at that. Oops. And so it's talking about this atom here, C00B, C00C. These ellipsoids are a lot smaller than the neighboring ellipsoids. And if you look at it chemically, does it make sense, you know, for a carbon, for an atom to bind to an iron ion, it needs a lone pair of electrons. And a carbon atom, a 3-coordinate carbon atom, to be honest, chemically, that doesn't exist. So you can't just have a 3-coordinate carbon atom and expect that to bond to an iron. It just doesn't work. If it needs to be sp3, it should have a hydrogen. So this would tell us it's not carbon, but it's something very similar to carbon, which, you know, very close to carbon, that would have a lone pair of electrons, would be a nitrogen. So let's go ahead and switch these to nitrogens. here. And that makes better sense chemically because now nitrogen has a lone pair when it's a 3 coordinate, and that can interact with the iron. So now if we click refine, if we did good, it should reflect in the R factor. And it did. We got lower R factor. We hit refine again. Refine one more time. And one more. So I'm just refining until I get to shift to converge to 0. Yeah. So this is good now. Now if we just do another check SIF, that error should be gone. So that's what you do. You solve your structure, you do a check SIF, you check out the errors that it gives you, go back, look at your structure, see if you can correct those. So we had one where the ellipsoids weren't good. So that told us, hey, we need to go back, look at our model. And we noticed, hey, this carbon with 3 bonds can't coordinate to an iron ion. So we go, what else could similar in size do that? It was a nitrogen. So the only thing I didn't show you on here was labeling the atoms. So you may have to, you'd go back and get the correct labeling for all the atoms. So if we scroll down, again, this alert level A is very easy to fix. You can find that information in the SIF OD file. And other than that, it's just some C level errors and G level errors. You can also go back and correct the Z value so that it fits the calculated. So we have a 2, they calculated a 1. And that's something you can go back and fix in the instruction file. So let me show you. So this is what I was talking about. So only the A error levels are left, which are very easy to fix. They're in the SIF OD file. So it was a long process, but we were able to model this slightly disordered solvent in the lattice. We also removed some of the solvent that we couldn't model correctly, and we made a mention of it in the SIF file. So I hope this was a very informative session.